Hello everyone, my name is Jae Shin and this is my final project for course mathematical modeling. Um, Especially this final project is about Monte Carlo simulation of traffic flow at a signalized intersection. It's from project 1, actually from chapter 5.5 our textbook. Over the next 10 to 15 minutes, I'll walk you through the problem, how I extended it, and how the simulation is built, and what it tells us about the delay, congestion, and how to time a traffic light well. Um, let's start with why this problem matters. Signalized intersections are the key bottlenecks of any urban road network. They meter competing streams of traffic onto shared road space, so they directly control how much delay drivers experience, how much fuel they burn, emissions, and even safety. That's why even a small improvement in how one busy intersection is timed can add up to real savings across thousands of trips a day. What makes this hard is that traffic is fundamentally random. Cars don't arrive on a neat schedule. They arrive at random, often in clusters, and each car takes a slightly different time to clear the intersection once the light turns green. Classic analytics formulas like Webster's can estimate average delay, but they rely on simplifying assumptions that rarely hold exactly. Monte Carlo simulation takes a different approach. Instead of solving an equation, we sample random arrivals and clearing times directly from the data, play the system forward in time, and measure what happens. And this ties straight back to our course. It's really an extension of the harbor unloading model where ships wait for a dock. Um, here the ships are vehicles and the service facility is the intersection, except service only available while the light is green. Okay, let's go next slide. So problem statement. So here's exactly what I set out to simulate. My case study is the northbound approach of a four-way signal. Um, I will call it Main Street and Oak Avenue. Vehicles arrive at random, queue up while the light is red, and discharge through the intersection on green at the measured saturation rate. The central question is, given those random arrives and the fixed capacity set by the signal timing, how do three things behave? The average delay per vehicle, the queue length over the time, and the throughput, meaning how many cars clear per hour. Mm. And just as importantly, how do they change as traffic gets heavier or as we change the signal timing? Our major goal was to make the algorithm visual, so the simulation animates every arrival, every queue update, and every discharge with the metrics updating live. Keep these three metrics in mind: delay, queue, and throughput, because everything that follow comes back to them. Proposed improvement. So the baseline textbook problem is fairly minimal. Single approach like fixed timeline, report average delay. These are not proposed by the problem in the textbook, but this is an assumption the textbook is uh, generally suggesting. So I extend it in six ways. First, instead of assuming arrivals are uniform, I, sim- I sample inter-arrival gaps and discharge headways from the actual empirical distribution of the data using inverse transform. Second, and most impactful, I generalized to a two-phase intersection with competing approaches and added an actuated demand responsive controller to compare against the fixed time plan. Third, sensitivity analysis. I sweep the arrival rate to find the exact load where queues stop being stable. For signal timing optimization, I search over cycle length, scoring each candidate by actually rerunning the simulation. Fifth, because Monte Carlo output is itself random, I repeat every scenario many times and show the estimate conversion. And sixth, the whole thing is wrapped in rich visualization. I will show results for all of this. Methodology. Let me explain how the simulation actually works. So, at its core, each approach is a first in, first out queue with a single server, and the twist is that the server is only available during green. Um, Traffic engineers call this a vertical or point queue. For random numbers, I use a linear congruential generator, the Park-Miller minimum standard. Um, yeah, yeah. I did some research about the Park-Miller uh, minimum standard, and then yeah, this is linear. This is one of linear congressional generators. It produces uniform numbers between 0 and 1. Then turn those uniforms into realistic arrival gaps and headways, I map them through the empirical cumulative distribution of the field data. That's the inverse transform technique. The heart of the model is the one departure rule on the right. Mm. A vehicle departs at the maximum of two things: its own arrival time and on one headway after car after car in front of it left, or wrapped in this function g, which says if that moment falls on green, fine. If it falls on red, push it to the start of the next green. That single rule captures the entire Q plus signal behavior. From the headway and the green split, I compute capacity. Green over cycle time, saturation flow, and the degree of saturation x, which is demand over capacity. X equal to 1 is critical threshold. For parameters, saturation flow is about 1,750 vehicles per hour, demand about 490, a 70-second cycle with 27 seconds of effective green. And critically, I evaluated the model three ways before trusting any output. The sampler reproduces the input data, throughput is conserved, and the simulated capacity matches queuing theory. Okay, visual simulation. This is the part I really like. I use Jupyter Notebook and it has a full live animation. Um, I pulled out 6 frames so you can see the logic. Read it left to right. Uh, in the first 2 frames, the light is green and you can see the queue draining. It goes from 4 vehicles down to 0 as cars discharge across the stop line. Then the light turns red in the third frame and watch the queue reveal 0, 2, 3, 4 vehicles because nothing can live on red. Every element here is driven by the simulation. The signal head change color with the phase, Cars stack up behind the stoplight, and in the live version of the clock, queue count and throughput are updated in real time. This build on red, drain on green cycle is exactly what produces the delay we are about to measure.